again, guys.
All right.
Is that like your new shut up thing, where like you cut instead of like just shouting shut up, you just talk everybody down?
Depends how loud the class is. I still got shut up in my repertoire. Why isn't this full screen? All right.
Question, why did you name yourself Parallels? Why would you name? Is it just like out of convenience sake, or?
When it installs Ubuntu with Parallels, I use Parallels, not VirtualBox. It automatically creates that user account as the super user account.
I was wondering.
All right, so last time we were talking about pointers and pointer math and how C++ gives us a special syntax for using these. At this point, we should have a pretty good idea. If I come over here and just pop open our things we've been looking at, where's our main.cpp? We were talking about those command line argument things that can come in here, same as in Java. What's the difference between C++ arrays and Java arrays? Go ahead. Tell me a little bit more. You still have to specify the length. This guy is a little misleading because we don't specify the length here because its length gets set by the command line that passes it in. Go ahead.
In the C++, can't you specifically choose where in memory you want the array to be?
Nope. Alloc is like the new keyword. It finds a place in memory for you. Or malloc. I think I showed you the example before. Go ahead.
The array can't report back to you how long it is.
Yeah, so arrays in C and C++, they have no way of telling you their length. They can't report their length. They're basically primitive types. Remember primitive types we talk about in Python and Java? Their primitive types are types that can only hold a value. That's the extent of their talents. Arrays are like that in C and C++. Whereas in Java, we've given some additional abilities to arrays because arrays are governed by an array object in Java. So in C++, arrays can't tell us their length. So that's why this main method here takes in two parameters. The argument count, how many elements are in that array, and then the argument values, the values of the array itself. Make sense? Okay, so that's an important distinction between Java and C++ that we need to remember because arrays are going to be a relatively common common thing that you'll use as a C++ developer. And here, starting today, we're going to start talking about our linear linked data structures. So we're going to kind of be looking at a alternative to arrays, and they'll have whatever abilities we decide to give them. That'll make more sense as we get into it. But a thing we need to remember is that the default arrays in C and C++ do not support length. There are arrays in the standard template library as well as newer libraries. So for today, everybody looked at the differences between kind of old school C++ and the latest C++, was it C++ 18, 17? 17. Kind of seeing what's happened to the language, not necessarily along the way, but from standard up to what the current one has. And one of the things you should have found is the current rendition of C++ has some extra stuff thrown into it that makes it a lot more Java-like. Things that we've come to accept about Java can now be used in C++. Some of those I've been exposed to, some of them I haven't. So, if you see something that we're doing and you want to give me an upgraded version of it, I'll use that, whatever makes you happy. Go ahead.
Well, through research, we also found that there's some things that it simply still can't do that Java can do, like the automated garbage collection.
Yeah, so what is automatic garbage collection?
It takes out like, I just wrote this paper. I just mentioned it was like it's like unused memory basically. It takes it out.
Okay, so when we create a new object in Java, random r equals new random, or like here we're creating a dice object, right?
Right.
New memory gets generated
That's right.
from that. Okay, new memory gets allocated. Remember we talked about in Java that new keyword is like our real estate agent that goes and finds somewhere in memory for this to live there. And we talked last time that something we can do in C++. I think I showed you an example of it, didn't I? Did I show you anything with malloc in it? Yeah, here. So, this is kind of like our new keyword. I actually think in C++ it's alloc. In C it's malloc, memory allocate, but as we get into it, we'll bump into whatever the syntax is, and that'll just be what it is. But we're allocating memory for this many of these guys. So we talked about the difference between I think it was your question last time, why does it matter what kind of pointer we're creating an int versus a char, because they have different sizes in memory. But in any case, when in C++, when we use malloc, which is our version of the new keyword, memory goes and gets found just like it does in Java. The difference is that Java has kind of like a dump truck that drives around in memory and looks for unused memory that we have finished with. Maybe we had a method that defined an object, and now that method has ended. Java's automatic garbage collection will go through and find that abandoned memory chunk and reclaim it so it can be handed out again by the operating system. So it's a convenience for us, but at the cost of performance, right? That's a computer program that's running, that's taking some CPU cycles, that's using a little bit of your computer's memory. It's not a lot, but it's something. And you have enough somethings that add up that will slow down the program. In fact, it's not the case now, but if you were an iOS developer in the very early days of iPhone using Objective-C, the Objective-C 2.0 language does support automatic garbage collection, but it was purposely disabled on iPhone so that your apps felt as performance, had as much performance as possible and didn't have this extra process running in the background. So in languages like C++, we need to effectively clean up our own room. If we create memory, we then need to delete that memory. I'm pretty sure in C++ the value is called delete. So we'll delete D there. Is it not like the way I'm calling that? It's not that kind of D, it's star D. C++ delete memory.
You're taking me to dinner?
Huh?
Taking me to dinner? You shouldn't have.
Oh, I use OpenTable all the time. Oh, we didn't use the new keyword, so we're not going to be able to delete it.
Wait, so even though malloc is the
I used malloc in our slides, not when I created the thing in our code that I'm trying to show you now.
So malloc, so that's what you meant by new keyword. So it's because okay, I thought you guys specifically used a new keyword, but you're just using that. You're saying that if you use malloc, it's
Oh, I can like that. Yeah, it must be a pointer to a complete object type. So this guy here, I'm creating a little bit funky. I'm letting C++ manage the memory for that rather than me directly doing it. So I'm at the mercy of the compiler, which doesn't support automatic garbage collection, but it's possible that Linux will clean it up for me. we'll circle back on that. But in general, in C++, we and C, where we are in charge of cleaning up our room. If we make a mess, we have to clean up that mess. Java, we don't have to do that.
So you recommend that if you use malloc, that at like the bottom of the code, make sure you put like the delete command for that object.
Not even recommend. That would be the correct way of doing it. Otherwise, we have something called a memory leak.
Yeah, that's.
Yeah, so
Like,
effectively what you have is your program has abandoned, you've thrown t-shirts all over the place through memory as you've run your program, and now all of a sudden the operating system doesn't have the ability to hand those places in memory back out. Yeah.
So automatic garbage collection is not necessarily a good or bad thing. It's just something that Java uses that makes it easier for the programmer, whereas C++ doesn't use it. It makes the programming more fast as a result.
Yeah, I think that's accurate. Yeah, so then you can decide if that's a good or a bad thing. Do we want convenience as the human being, or do we want to have to clean up our own messes at the cost of more performance? Realistically, today's computers are so fast that that automatic garbage collection is probably okay. But if you think about the types of applications that C and C++ are used for, if we just talk about like video games or operating systems as like the primary place for them, those are things where we want to get absolute maximum performance out of those. And with that in mind, it probably makes sense not to rely on it to do automatic garbage collection and instead clean up your own messes.
When you terminate the program, even if you haven't freed up the memory, it automatically allocates it back, right?
That depends. It depends on the operating system you're in the runtime. So some operating systems, most newer operating systems, will run a user program in user space where you can have all the memory leaks you want while the program's running, but when the program ends, it'll give the memory back. Some older operating systems, when you run a program, it loads the program into like shared memory, where this would be less secure. So modern operating systems kind of put things into like little pods, where the pod lives and dies on its own. But if we were dealing with a little bit older operating system or a less secure operating system, and it loaded into shared memory, and you had claimed memory location 100, let's say, and you didn't clean it up, that memory location 100 would not be able to be handed back out by your operating system until you rebooted your computer.
So like when you run top on a Mac terminal, and it shows like.
Well, top shows running processes.
But it shows like the user.
Amount of user memory that's available, yep.
Yeah, so that's what you're talking about right there?
Well, I mean, if you will reduce the amount of usable memory on your system if your program is either currently running and you're using memory, or you're running an older operating system where the program has ended but you didn't free up the memory, so you just left that t-shirt living in bucket 100. Okay? Even though you have no way of accessing it anymore, you've lost the pointer to that, which we'll talk about some today. You've lost the pointer to that guy, so nobody can access it conveniently. You could walk through memory and maybe stumble upon the t-shirt, but nobody can conveniently get to it. So you've lost your opportunity to tell the operating system, I'm no longer using this space. Go ahead and mark it as unused so that later on, if somebody asks for some memory, that's a legal place you can hand them. Otherwise, in an older operating system, if I didn't personally delete it and I didn't actually tell the operating system, either me telling it directly or the program finishing execution, cleaning up all the memory, at that point, now that's an unusable bucket of memory that the operating system will not hand back out until you've restarted your computer, and that will clean up all memory and then reload the operating system into memory. Go ahead.
Can you delete memory that you aren't even using in the code, like outside for other programs?
No, you have to have control of the memory. Historically, there was probably very, very, very old renditions of operating systems where, in a language like C, where you have, in C++, where you have a lot of control over memory, you may have been able to take a walk outside of the memory space that you were working in, create a memory address, and use math to get it to go to a very specific place, and do stuff with it, make changes to that memory. The same is technically still true. If you can get to a place in memory and it's technically in user space and the operating system hasn't kind of put your program running inside of a bubble, you technically can get to other memory places and possibly overwrite them and do bad things, stuff like that. But you would have to be with intention. You have to purposely like go to some place in memory, then add 1,000 to it. Now you're somewhere else in memory that may not be anywhere near where your program's actually using. Go ahead.
Oh, so I was going to say, do pointers and the automatic garbage collectors perform the same task, essentially? It's just a matter of...
Well, the pointers point to a place in memory. Automatic garbage collection would remove places in memory when pointers no longer point to them. So a place in memory has what's called a pointer count. So we're going to see this when we start dealing with linked lists here. You might have 2 or 3 different variables that all point to the same place in memory. Once that number of variables goes down to 0, nobody can get to that place in memory. Java, with its automatic garbage collection, walks through memory and says, what's the pointer count of this bucket in memory? And if it reports back that it's 0, meaning no variables point to this guy, it then frees it up. Whereas C++ won't do that by default. So you can get to a 0 pointer count, and that memory is still being flagged by the operating system as being used. The reality is in C++, though, if we want to be able to delete memory, our pointer count would still have to be at least 1. You still have to have a way of getting to that memory to tell it to delete that thing in memory. And then it would count it down to 0. It would clean up that final mess. All right, and we'll look at some examples. I'll get the correct syntax for it. It's not difficult. It uses the delete thing, but right now I'm creating my object in a kind of like last semester when we were talking about strings. When you say string s equals hello versus string s2 equals new string hello, where actually we are requesting memory somewhere else. This is creating a dice literal in kind of protected memory that we don't have control over. I presume if we're doing this because programs run inside of little pods that we're actually protected and it's going to get cleaned up, but not by the mechanism of automatic garbage collection, but more by the mechanism of the operating system saying, your main CPP program has finished running, so any memory that it's using is now gone. But that's not a function of C++, that's a function of the operating system running your program inside of a little bubble. And when your program ends, it just reclaims anything that bubble was using. Does that make sense? All right, so, and with that in mind, the difference between automatic garbage collection and C++, well, not even C++, Linux, for example, running your programs inside of its own little bubble. The difference there would be during runtime of your Java program, automatic garbage collection is cleaning up memory. Whereas during runtime of your C++ program, that memory being taken up by that variable D right there is not reclaimed. It's currently being used, and it's used until this program completely ends. Make sense? So we're technically maybe using more memory at a particular point in time in C++ than we might be in the equivalent Java program, because if we're not cleaning up our own messes, that memory sits there until the operating system reclaims it at the end. Okay. In C++, the rule of thumb would be we should, as good programmers, manually delete our memory. Okay, and we'll look at how we do that. Okay, so this reads something in. So this is kind of like our scanner. This creates a new object. We're going to eventually start using the allocate to actually specifically request memory. This goes through and it rolls our object. This stuff should start looking pretty familiar. This looks identical to Java. This looks identical to Java. this system.out.println replacement is a little bit funky, right? We are sending output, and then we can kind of do concatenation using this less than syntax. So we're saying roll this value, which is the number, concatenate onto that a carriage return. Actually, that's a line feed, but most operating systems today treat it as a carriage return and a line feed. Historically, you would have needed a /R and a /N. /R says carriage return, /N says feed the line to the next line. And then ultimately at the end, I'm returning 0 because I've advertised that main returns an int. I could have made main return void here and then not returned anything there. And that would still work. All right, so historically, because C and C++ have been used for writing, let's call it Linux tools, you might call upon a function where you expect it to give you a result when it finishes. And a lot of times that result is a numeric result for like an error code. If you've ever been on a web browser and a website doesn't load or something, you get like a 401 error or something. You know, different numbers mean different things. And a lot of times an error code of 0 means everything went peachy. An error code of something other than 0 might mean different things. Right? You can go with the 0 or 1 and just say it worked or it didn't work, or you can have 5,000 different integers that you return that mean different things broke. All right? Because we don't have a convenient way of exception handling in C++, or at least not an evolved way of exception handling. Okay, so let's start talking about linked lists. I think we talked about them a little bit at the end of last semester. So we're going to talk about linear linked data structures. So a weakness of arrays is that we must declare the size of the array at the beginning, and changing the size of the array is destructive and not memory efficient. Right? The idea would be that you build a house, the house has a certain amount of square footage, you decide you want to add on an addition, you want to add a porch or something like that. You know, the array example of this is build a brand new house that's a duplicate of the original house with a little bit more space for your addition. Move all your crap from the old house over to the new one, burn down the old house. Or in C++, you can choose not to burn it down, just leave it abandoned there in memory. All right, so you get that option. So you can imagine if you, especially in a language like C or C++, if you are writing something that starts with a small array and you just keep adding buckets to it, you know, through an object or something where you're constantly like leaving abandoned houses in the back and never cleaning it up, you end up starting to take up a lot of memory very quickly, right, in your operating system, because you're not cleaning up that mess and there is no automatic garbage collection to clean it up for you. All right, go ahead.
Does leaving memory like that completely like slow down the computer process? Is what you're saying?
Well, it won't slow it down. It just reduces the amount of RAM that your computer has access to. So, I mean, if you have plenty of memory in your computer, you may not notice for a long time or even ever. But it would still be a bad idea. I mean, it's no different than if you leave a t-shirt on the floor in your dorm room. Maybe one t-shirt's not the end of the world, but by the end of the semester, if you have 700 t-shirts on the floor in your dorm room, you know, and you have to like, you know, not that you own 700 t-shirts, but now traipsing, if you need to find a place to throw your today's t-shirt, you might not find an empty bucket.
I see. Okay, that makes thank you for the analogy. That makes sense.
Yeah, your computer doesn't care how much free memory it has, as long as when it needs memory, it has access to it.
Yeah, it's like completely like
And when you take the operating systems class, one of the things you talk about in there is something called virtual memory, where it fakes extra memory using your hard drive, which would be considered very slow. memory. So you'd rather have things in real memory because then it'll feel fast. But if your real memory is too filled and you have to start using virtual memory, your machine will feel a lot slower. All right, so linear linked data structures. The idea is that it's not that arrays are bad. Arrays have a weakness in that when you create an array, you create a collection, you have to know at the beginning how many things you're going to store, or at least decide you're going to trade off memory efficiency and say, you know what, I know I won't have to store more than 1,000 things. So I'll go ahead and create an array of size 1,000 and I'll just fill it up as needed, knowing that at worst case, I will have wasted 1,000 buckets of whatever kind of thing I'm storing. All right, so you're taking up a place of memory guaranteed that you're going to be taking up as long as your program's running, and you may not fill it, but you're at least giving yourself a big enough basket, kind of like building a house on a huge plot of land. Even though the house might not take up anywhere near the whole plot of land, you've given yourself room to expand, something like that. All right. Now, with that in mind, we're going to say that arrays are really fast. And they're really fast for the reason we talked about last time, is we can calculate the location in memory where where a bucket of an array lives, because arrays are stored in what's called contiguous memory. Remember that from last semester? So because they are stored in contiguous memory and we can calculate the exact memory location of a bucket in the array by using the base address and adding the bucket number times the size of the type we are storing. So we can effectively kind of teleport to bucket 8 in an array if we know where it starts and we know how big the things are in there. We can just boom, teleport to bucket 8 of that array by taking the base address and adding to that memory address 8 times the size of whatever we're storing. That make sense? So for those reasons, and because arrays are stored in contiguous memory, we have the benefit of speed with arrays. That make sense? All right, now linked lists, let's just we'll just ask the question here. What if we need to arbitrarily expand or shrink? And I'm going to put in quotes here, an array. We're going to be looking at a replacement for an array. And don't want to destroy memory. We'll put a little note. We will need to give up speed. But keep in mind, like we talked about already today, giving up speed in today's computers isn't necessarily a bad thing. It can be in certain applications where we want everything to be as fast as possible. But our computers are so fast today that in most circumstances, giving up some speed at the benefit of better resource management or convenience or whatever is okay. We just want to make sure we're using the right tool for the job. All right, so we'll have to give up some speed using a linear linked data structure, but what we'll gain from it is the ability to have a single thing that can grow or shrink. All right, so with that in mind, we have something called a linked list. So a linked list starts off as empty with a pointer to the beginning of the list. And we can, say this is kind of like the base address. except linked lists will not be in contiguous memory. Or at least we're not guaranteed they'll be in contiguous memory. I suppose if the moon's aligned and you keep asking for more memory and it just happens to give you memory right next to the previous bucket, it might end up being contiguous memory, but I think that's extremely unlikely. All right, so a linked list starts off as empty with a pointer that points to the first element. So typically this pointer is called head. That is the beginning of the list starts off as null, or I believe C++ null is represented as either nil or null. I'll have to look at which of those two is in our current compiler. It's been both at some point. I just don't remember which one came first. So I'll put nil in there for now. You'll know that those are synonyms for each other depending on what language you're working with. Okay, and we'll pretty quickly, get those couple of syntactic details down as we're getting into this. This is kind of that evidence that the language does not matter, right? You learn the little quirks, and then from there you're just off to the races. All right, so head's the beginning of the list, starts off as null. Sometimes we use a variable called tail. This points to the end of the list. Now remind me, last semester, how far did we get into linked lists? Did we do any implementation, or we just talked about, we're kind of reviewing it here, but we didn't actually create nodes with next pointers or anything like that?
No, I don't think so.
Okay, good. That's good. So we're reviewing it here, and we're going to start writing the stuff here in a second. All right, so we have a head and a tail. Now, at the same time, sometimes we use a variable that we might call count. This is less official. Head and tail are pretty much common terms for beginning and end of, you read any data structures book, there'll be head and tail. But sometimes we use a variable called count that keeps track of the current number of elements in the list. This can come in handy because if we don't keep track of that like in an integer, then every single time we want to know how many elements we have stored, we have to walk the entire list and count. So we can calculate it by going from the beginning of the list all the way to the end of the list, counting 1, 2, 3, 4, 5 each time, or we can just keep track of a single integer, and whenever we add something, we increment count. Whenever we remove something, we decrement count. So this can be a convenient addition to our linked list that's only costing us an integer, right? All right, so that's kind of our baseline for a linked list. So now, in terms of the player, so we're thinking in terms of object-oriented programming. We want to create our linked list. Well, let's draw a picture first. So we might have a linked list that by default, so here we'll call this guy LL. That's our linked list, and we'll have a head. For starters here, we're not going to use tail. We're just going to use head because it makes it more difficult at the beginning, which is fun. And then we're also going to have a count. All right, so initially, head is null, and count is 0. And head would be a pointer that currently points nowhere. So when we first create our linked list object, we'll have something that looks like that. All right, so we need an object representation for that guy. So let's go ahead and let's just design that on a slide. So we're going to call this our linked list object. Linked list object is going to have a variable called head, initially points to null. It's going to have a variable called count, initially equal to 0. So as far as we know right now, that's what this guy has. All right, we'll grow it as we start drawing our picture. Now let's say we want to add a value to our linked list. All right. Typically, we might have a function called add front, or add end, or add at index. So this guy will add a value to the front of the list, i.e., head will point to it when it is done. Add end, add a value to the end of the list, i.e., the last element, or let's call it the previous last element in the list will point to it when it is done. Add index adds a value somewhere in the middle of the list, given its traditional zero-based index. Usually we would use zero-based index. That's how we think of arrays, right? Starts at bucket, array has a length of 10, bucket 0 to 9. Strings have 10 characters in it, bucket 0 to 9. So it would make sense if we're creating our own linked list and we're talking about a particular bucket number, a particular element in the list, that we would conceive of that in a similar organization to how arrays work, right? We are writing it, so we get to decide, but if we're already thinking about collections as being zero-based, we might as well make this guy zero-based. Buyer beware. Every now and then, you will bump into a programming language that treats its collections as not zero-based, but the first element is number 1. It's rare, but they do exist. So usually when you start working with a new programming language and you say, how do I remember things? How do I create variables? How do I write if statements? How do I write loops? You will then maybe follow up and say, okay, when I'm working with collections, how do I index them? That might be a follow-up question just to make sure you know how to work with that collection. Make sense? It's still a collection. Its length will either be, the last legal bucket will either be its length minus 1 or it'll be its length, depending on whether it starts at 0 or 1. So nothing really changes. You just have to adapt your logic by 1. But that is one of those idiosyncrasies of some languages that you want to be aware of when you're starting to work with a brand new language, although you can pretty high percentage of the time, let's call it 95% of the time, trust that it'll be zero indexed. It's pretty common. Okay, so we've expanded our linked list object here a little bit. So now we're keeping track of a couple of fields. So we're going to call these guys our fields, right? And then we have some methods. All right, so one of the things you guys are starting to work with, you're probably not too far in yet, but most of you are in the 370 class right now, right? Software engineering. And that class, while you'll do some programming in there, a majority of that class is the planning process for software. Now that might feel boring, okay? And I get it. But as we get to more and more complex things, and in this class we're doing a lot of things with memory, we're drawing pictures is going to be necessary and things like that, it will be in your best interest to plan it out at some level first, okay? So we are designing our objects here, not necessarily using the kind of the global project management stuff that you might do in software engineering, because software engineering is more focused on what if you're working in teams, collaborating with other people and things like that, because now you have different people with different roles, and how do you communicate so that you can efficiently get something done. But as an individual writing one of these, you might still want to plan it out like this, so you kind of have a paint by number, so to speak, when you go to start writing this. All right, so we have our linked list object. We've decided where we're going to remember some values, some variables associated with this guy. And here's some abilities we want it to have right off the bat. We're probably going to add some abilities to remove stuff too, but we'll start with adding stuff. Yeah.
All right. So to clarify the difference between a linked list and an array is that a linked list puts stuff everywhere and then makes it less efficient.
Yeah, and you're going to see it here in a second.
Grow and shrink more effectively, whereas a array list has a set length and it's more efficient because you can.
An array. Don't call it an array list. Array list was like a special thing in Java, but the array data structure is stored in contiguous memory and has a length. A linked list is not stored in contiguous memory and can grow and shrink. And we're going to see how it accomplishes that here in a second. All right, so now we have a representation, at least planned, for that guy right there. Okay, it is a linked list object that has a head and a count. And initially the head points nowhere and the count has 0 in it. There are no elements in this list. So now we start creating elements in our list. So here I'm going to say we're going to add a 5. And we'll just pretend that got put at memory address 100. And this guy will have a payload, which is going to be equal to, in this case, 5. And he's also going to have a next node, which by default will be equal to null. All right, and we're going to call these guys nodes. I'm like a keynote ninja. All right, so this is going to be a node object. And we're going to go ahead and represent our next node here. So just like head, next node points somewhere. So we decide we want to add this node object to our linked list. All right, so let's go design our node object here. So we have a node object, and a node object is going to have something called payload, which is going to be the value that this node will hold. So let's initially create a linked list of integers. That's usually our go-to move for linked lists. So we're going to have some fields, and we're going to have an int called payload, and then we're going to have a node pointer called next node. That is something that will point to another node in the list. Now that we've defined an object called node, we can go back to our linked list and we can give a type to head. Head is a node pointer, and we could have given a type to count before. Count would be an int. So the number of elements in a linked list will be a number. Int is good enough. That'll allow us to have up to 2.1 billion elements in our list. If we need more than that, we can make it a long if we want. This will be sufficient for us right now. And the linked list object points to the front of the list through its head pointer, which points to a node. hence node pointer. And notice here we're using the C++ syntax for pointers, node pointer, little asterisk next to it. A node object is going to have some fields. One of them is going to be the payload. This guy is the value this node holds. And next node, that is the next node in the list that comes after this guy, or after this node. All right. Now, we're probably going to have some values here or some methods here like get payload and get next node, set payload, or maybe set next node, something like that. But we'll leave it blank for right now. We'll add to that as we start getting in here. But this object right here represents this guy right here. So if we want to add this guy to the front of the list, we would make head point here. If we then have another node, maybe this guy has a payload of 7, and we want to add him to the, and let's just say his memory address is 200. So right now, head actually has a value of 100. Head is a node pointer. It points to a memory address. This is memory address 100. We point to that place. What lives at memory address 100? This node object, which has a payload of 5. It has a next node of null at the moment. Now we want to create another node, and this guy is going to have a 7 in it. And it happened to get allocated at memory address 200, convenient for us. All right, instead of crazy looking hexadecimal thing. And plus it fits in the little red box I made. All right, but not right next to it, not contiguous in memory, okay, another place in memory. So we have this node, and we want to add this guy to the end of our linked list. So we go to the head, we traverse our linked list to the end. So this is the last guy on our list. We know because his next node points nowhere. And we set his next node to point to the node we just created. So that guy now points to memory address 200. And this guy still points nowhere. That make sense? So this is what a linked list looks like. If we want to remove something from this list, we can say, oh, I want to remove the element from the end of the list. Okay, what does that mean? Well, I need to get to the end of the list. Right now, we don't have a way of immediately getting to the end of the list using tail. So we have to inconveniently start at the beginning of our list and walk the list from node to node to node until we get to the last node. Now we're also going to have to keep track of the guy right before the last node because we need to be able to disconnect this right here. All right, so I'm going to find my way to the current end of the list. Well, we're going to find my way to the guy right before the end of the list. Then find my way to the guy at the end of the list. I'm going to tell the previous guy, well, I'm going to remember where this guy is. So I'll have to, let me just show you this as an example. This is related to what we were talking about earlier. If I get to this point right here, and I go ahead and set this guy's next node to null, nobody currently points here. He's lost. Java would automatic garbage collect him, which also is not what we want because we probably want this value. The reason we stored it in the list is it's a value we intend to use again. Okay, but right now, nothing points here. We've lost that value. We have to be very careful with that when we're working with memory. So realistically, we're probably going to have a variable maybe called curnode or something like that. That's pretty common. That will start off at the beginning of our list and traverse our list until he points at the very last guy. That is the guy whose next node is null. And maybe we then also have a almost last, something like that. And this guy always drags one behind cur node in this case. Because we definitely don't want to update this pointer head and walk along our list, because now we've lost the beginning of the front of the list. So one of the defenses we need to have when we're working with memory like this is make sure that any object that you have always has at least one pointer pointing to it. And before you disconnect something from it, make sure that's what you really want to do. If head is supposed to always point to the beginning of the list, you should only change the value of head when you're changing the front of the list. Don't use head as this magical way of traversing your list and just keep updating it, because now nothing points to the beginning of the list. Right? So instead, give yourself this extra variable. So we're going to have both of these start at the head, and we'll write the syntax for this in a bit. So we'll have both of these point to head, and then we'll say, does next node equal something? It does. So there is a next node. So we'll go ahead and have this guy point to something. Then we'll ask the question, does this guy's next node point to something? In this case, it does not. If it did, then we could safely have this guy follow. But since it doesn't, we know this guy's as far as he needs to go. He's one behind. All right. So we have kept track of the guy right before the end, and we've kept track of the guy at the end. Okay? Now we can safely tell almost last to set his next node to null. Because we still have an anchor connected to this guy. We still have access to him through this variable right here. And we can do whatever we want with it. Go ahead.
So say you wanted to use the add at index with the linked list, and you wanted to put it between those two nodes, you would have to adjust like 3 or 4 pointers, right?
Yeah, you got to draw pictures. Be careful. Yeah, we're gonna do that, but this is the easier thing. Actually, the easiest one is remove from the front. That's just minor surgery. But yeah, adding or removing at index somewhere in the middle is it's probably still outpatient surgery, but you're under the knife a little longer probably. Okay, definitely draw your pictures. All right, so you kind of see how this is working. So it's kind of cool from the perspective that we're directly manipulating memory, but we also need to be careful, right? If we want to add something, we need to traverse our list and tack it on to the end, or we just tack it on to the front by updating, our node. So for instance, if I want to create another node here, and I want this guy to be the new front, I'm just positioning him over here. He might be memory address 300, so it doesn't just because he's the front doesn't mean he's any earlier in memory. And we'll make him the value 9. And if I want to add him to the front of my list, I know where the front is, don't I? The front is where head points. Real easy to get to the front of the list. But can I just immediately do that? Because now, here, let me move these couple of pointers out of the way. These are for later. All right, so if I change head to point to this guy, now all of a sudden nobody points to this node. I've lost the old head of the list. So what do I need to do first? It's an order of operation thing. Before I can make head point to a new place, I need to have my new guy, which presumably is stored in a variable that I created a new node called n. He just came into existence, and now I need to connect him. So something does point to him. So I need to make him point to a next node. So this guy points to 100. Now I can safely connect head to him. So head points to 300, which points to 100, which points to 200. That make sense? How linked lists are functioning? And these guys are strewn about memory. This guy lives at bucket 100 in memory. This guy lives at bucket 200 in memory. This guy lives at bucket 300 in memory, not contiguous memory. The other nice thing about this is now we can potentially store more values in memory, because when your operating system is using the system's memory and scheduling for it, it's going to, when you request 100 bytes of memory, for instance, it has to go and find a chunk of memory in a row that's 100 bytes. So if you've been running your computer for a while, you have a whole bunch of applications open, and you took a snapshot of what memory looks like, you might see these little tiny pockets of memory throughout your memory that maybe you only have 70 bytes in this little pocket. So unless you're requesting something at 70 bytes or less, this might not be a viable place to put it in memory. That make sense? Or in this case, we only need a pocket of memory big enough to hold a node. So relatively small. And we can place a node here in a little tiny pocket, and a node here in a little open pocket of memory, and a node here in a little open pocket memory, and have them point to each other. So it's more efficient to strewn the portions of our list throughout memory, because we don't need one giant footprint like an array needs to store it contiguously. Okay, so we're gaining memory efficiency, but we are losing performance, because if we need to walk through our linked lists, we can't just calculate where bucket 6 is and teleport there. We have to walk from bucket 0 to bucket 1 to bucket 2 till we get to bucket 6. Make sense? Computers are really fast. We probably won't notice as humans that time it takes to traverse, but it is a voyage instead of just teleporting there. All right, questions about that? All right, so we have a decent idea on what a linked list looks like. Okay, and we've kind of visualized these guys in terms of our objects. So this is our linked list object. This is our node object. I've made nodes bigger because of the yellow box, but they aren't necessarily bigger, just this is how I've depicted them. But we have two objects. If we think about this like a play, right? We have two objects in our scene, two actors in our scene. Go ahead.
And will count be automatically incrementing, or is that?
Yeah, sorry. As we added these things, I would have incremented count, so count would have become a 3.
Would that do it automatically? You wouldn't have to.
Oh, no, that's our code.
Okay.
No, we chose to put count in here. That's our object right here.
Gotcha.
We chose to have a field called count. If we don't want to change it, it's not going to change. Yeah, most programming languages do have linked lists built into them. C++ does in the standard template library. Until further notice, you're not allowed to use it. You have to write your own linked lists. Because that's what we're learning how to do here, is work directly with memory and writing these things. So yeah, if we want our linked list to keep track of how many things are in there, we got to change it. Somebody calls one of the add functions, count goes up. Somebody calls one of the remove functions, count goes down. All right, so now that we've designed our solution, or at least a starting point for our solution like this, and we're thinking about this like a movie or a play, we can see that we have two actors involved here that we have to bring into existence, right? And we've kind of designed our two actors at a fairly high level right here. So now we can go write the code that makes this a reality. Make sense? So we'll start with this. So we'll come over here and let me do this. So inside of my 300 folder, I'm just going to make a directory called, we'll call this guy linked list. All right, and we're going to create our new files inside that directory. So we have a little organization here. All right, so what I'm going to do as a starting point here, I'm going to steal this code, and we'll modify it for our linked list object. Actually, let's create our node first. So I'm going to create a new file here. I'm going to go ahead and save this guy as node HPP, but we're going to put this inside of our linked list folder. So this is going to be our header file for our node object. Okay, and while we're at it, I'll go ahead and create our node CPP, the implementation of that header file. So we'll have node.cpp in there. I'll also go ahead and create a new file. This is going to be LinkedList.hpp. And I'll create a new file, LinkedList.cpp. All right, but we're going to start off with our node HPP here because we've copied our dice HPP as our starting point. So I'll paste this in here. All right, and this guy is called node HPP. Node HPP. These are directives to the C++ compiler that says if we haven't defined this guy, go ahead and define this guy. This is to the linker. All right, we'll go ahead and still include standard io.h in case we need to do some IO stuff, although right now I don't necessarily see where we're going to have to do that. In fact, I'll take it out right now. Let's keep it as bare bones as possible. Go ahead.
That's .hpp, right? Not like the little slash under.
Dot isn't legal in here, so underscore is the syntax
Well, no,
for this
I'm talking
macro.
about, like, the file name.
File name is node.hpp.
Yeah.
That's the extension of our file.
Right. That's what I
Yeah, nothing special here. HPP is the MIME type for these files. It's a C++ header file, but it's just like a .docx, .java. It's a dot extension, just like every other thing.
All right.
The name of our class is called Node. We're going to have a couple of private. We've talked about public, private, protected in Java, and we mentioned that we should make things private and then loosen the reins if we have to. So we've decided that for our node, we're going to keep track of an int payload and a node pointer called next node. All right, so we'll have our int payload, and then we're going to have a node pointer next node. All right, now right now, we have no public functions that we've defined, or public anythings, because you can have public fields as well. But right now, as we've designed our node, it has two fields. All right, so this is the header for this guy. So now if we look at dice CPP, we see that we have a constructor for this guy. So I'll go ahead and just copy this. And we're going to go into node CPP. We'll paste this in here. And we want to include node HPP. Now notice I have this guy in double quotes. What does double quotes mean around it instead of the angle brackets? Go ahead.
Like local memory?
Yeah, it's one of our files. Local, current directory. So that's our invention if we put double quotes around it. The angle brackets means this is one of the global libraries that come with C++. All right. Again, I'll go ahead and get rid of these extra libraries. We might add some stuff back in, but for right now, we don't need them. So let's keep it as streamlined as possible. So all this guy needs to know about right this second is what he is actually implementing. So he is implementing the node objects constructor, which is the node. And he's going to take in a payload as a parameter. And he's going to set this guy's payload equal to the payload that was passed in. And then I'll take out this line here. And we don't need any of these things right now. So there's our constructor. Actually, real quick. I wonder why it's yelling about well, we'll come back to it. It's fine. Did I mess something up in my node? That guy has to have a semicolon at the bottom of it. No. Put that in there just to make it match. Yeah, we'll figure out what's going on with that. Could just be that Visual Studio Code is making it weird. Although it's not giving us an issue here. No, takes in a payload. Oh, sorry. If we want to write a constructor, we have to define our constructor. So in our public thing here, we have to advertise. If we're going to implement it, we have to advertise that we're going to have in this case, it's a method, but it's called node, and it's going to take in a payload. So we've said this is going to be a public method named node, and now over here in node CPP, I can now define from my node class, I'm going to define my node public method to be something that takes in a payload, and now all this stuff works. So again, the idea of your header file is to display kind of like a quick documentation of what a node is. If we look at this guy right here should look pretty similar to what we've done here. Kind of a skeleton implementation, okay? But in Java, we get a no argument constructor by default. Now in this case, we don't want a no argument constructor. We actually want a constructor that does take in a single argument. Well, if we're going to do that, we have to advertise it in our header file. We have to say, one of the things this guy has is a collection of constructors. In this case, we have one. This constructor is called node, and it's going to take a single integer as a parameter. Then over in the node CPP file, this is where we're implementing the things advertised in that header file. This is where we actually write. We implement that constructor. And what do we do in here? We set whatever payload was passed in equal to this particular guy's payload. And what's this keyword? What does this refer to? Go ahead.
It's like referring to itself from within itself.
Yep, so how does an object refers to itself from within itself? What was your other question?
How come we have to add a semicolon at the end of the header class definition, but we don't have to add the semicolon in the
Okay, yeah, because this is a prototype class, so this is actually going to be read in as a statement by the compiler. So if you do the 470 class, we talk about language design. As the compiler is going through and parsing this file, it's going to look at the end of this for the end of that statement.
Okay.
Where a class definition, this guy, or an implementation definition, this isn't even in a structure. These are connected to those implementations. So when we compile this and then ultimately link it, so we have two steps here when we compile code. And this is true of any compiled language, actually. So compiling code. A compiler first converts from high-level language to low-level language. So in our case here, from C++ to x86 assembler. It'll probably actually be i386 assembler, but assembly language. Then we have a linker that combines the assembly files into an executable. And the default executable, if you don't give it a specific name, is a.out. So that's actually so a.out is the default. That's the output of the linker. That's your actual executable file, and that's after it's combined all of your compiled files into a single executable. So by us separating these files into two separate files like this, we didn't have to. We could have written it all as one file. But by us separating them into two separate files, we're able to, we link these two files to each other through the include, and then we're saying that we are implementing the node class's node method. So that first node, the one that's in the green, refers to this guy right here. This node piece right here says which of his members are we implementing, which is this guy right here. Does that make sense? So at the end of the day, all this stuff here will end up getting sucked into this code here.
Okay.
All right, so that is our starting point for Node CPP and our Node HPP. Similarly, we want to create our file for our linked list HPP. And our linked list is going to have a node pointer called head. And it's going to have an int called count. We will have a no argument constructor. All right, notice this guy doesn't know about node, so we need to include node HPP. And now he knows about the node class. Go ahead.
So for my node HTTP file, my node pointer next node isn't complete like that. Is that because I don't have the CPP class yet? Is that why?
That's why. Yep. All right. So for Tuesday, get your node and linked list classes created. Now, we're not going to be able to test this yet, but also attempt to write the code for node and linked list and implement the code within linked list for adding a value to the front of the list. You can use the dice example for creating an object for now. Now, you can choose to go and write main to test this, but really I want you to draw pictures and make the right moves with your code. So I'm not actually going to run your code, so errors might be okay, but I want you to start by creating a public function that will be add front, and then trying to make the right moves where you disconnect head and you connect up you create the new node, disconnect head, make the new node's next pointer point to this guy, so on and so forth. Make sense? So just a little bit farther than we've gone here. and that'll be due on Tuesday. Yeah.
And just want to make sure, would we define the methods in the .cpp and just basically like the constructor and the
No, you would still, so in linked list here,
Uh-huh.
you would have a add front, and you might take an int payload here, like that, and then over in CPP, you would actually implement
Okay.
that guy where you would create the new node
Okay.
and start setting the different things. Yeah, so this guy should always be kind of an advertisement of what this object's capable of doing.
And would you need the type in front of it?
Yeah, so this guy's gonna be void because he's not actually gonna return anything.
Got it.
There's another question over here. Good. All right, I'll see everybody on Tuesday.